Hello, everyone. I think now it's time to begin the class for today. And I just in the chat, I just share our today slide one more time. It's the same with the first one I previously sent in the chat, but maybe some of us just join the class, so I resend it again. And another file that I sent in the chat is the PDF file of the textbook, The Introduction to Robotics by Craig. And in our class, we don't have much time to go deeply in the detail for the derivation and for the extensive explanation of the theory. But I will try to provide you some equation and give you an idea how to use the equation. But if you want to go into the detail of the derivation and to see some example, you can check in the textbook file. And if you have some question when you read the book, we can have the further discussion. And let me share the slide. Okay, now I hope you can see my screen. So our today's topics is the position and orientation analysis. And maybe the content today is a kind of the boring things, just only metrics and the mathematical equation. But the content in today's class is very important for our next week study, because in the next week we will try to apply the basic concept that we studied today in the example of the industrial robot. So today we will have some introduction to the basic concept of the industrial robot and give you some notation, so that when we read the textbook or when we see the equation in the slide, we can understand it in the same way. And yeah, the industrial robot is a complicated structure. It has a lot of it has many links and joints, and the robot are built in the complicated shape in order to deal with the robot problem. And if we want to solve the problem by using mathematical tool, we need to try to model the robot link and join into the form that we can have the calculation on paper or apply to the computer system. So the form that we try to represent the physical robot in the mathematical explanation, we use the metric. So the robot, they have many links and joints, and all the moving things, we try to attach the frame to each moving things. And on the frame, we will have many points, which are the physical point on the robot part, but the point will be described with respect to the frame. And we also consider the orientation of that frame. And today we will get to know about this concept, how to compose the metric representation of industrial robot. And when we talk about the orientation of the frame, in the past, when we study our basic subject, our basic class, we may familiar with the frame that maybe XYZ frame that fixed to the global coordinate. But as we know that the industrial robot has many links and many joints, and we have the reference frame in the global coordinate, but all the joint also have the relative motion. And maybe if we want to graph the thing on a table by using the gripper, maybe it's easy to relate the object to the gripper directly. But how can we control all the joint from the base frame to the first link, the second link until the gripper? How can we relate this to the coordinate on the gripper frame? The frame has different position and also have different orientation. The idea of the angle that try to explain how is the relative angle, relative orientation between the different frame. We will talk about that in these two types of the relative angle. Before this, we will talk about the rotation metric first. In the rotation metric, it's a 3x3 metric and have 9 components inside. If we want to talk about the rotation metric, we need to talk about 9 components in the matrix. But for the angle representation like this, we just need only 2 or only 3 variables to describe the rotation metric. And we will try to talk about the relationship between this angle and the rotation metric. And yeah, as we mentioned that the frame in the global coordinate, we have many frames. And if we try to explain that frame, the frame have the origin of each frame are different in position. The origin are different in position. And if we want to relate the frame, we need to know how the distance between the origin of the frame. And we need to know how the orientation of the frame different. So we are talking about, we need to translate the origin of the frame to somewhere. And we also need to rotate the frame to be in the direction that we want. And we have the mathematical tool to map the translation and the rotation of the frame. And actually for the position, we know that yeah, we have the position in X and Y and Z direction. And the dimension of the metric, the vector, yeah, we can see it as a metric, 3x1, right? But if the number of column is 1, sometimes we call this is a vector. So position vector is a 3x1 metric. And for the rotation metric, we have 3x3 metric. The homogeneous transform is the tools that combine both the position and the orientation in the same metric. And the dimension of the homogeneous transform will be 4x4 metric, which is composed from the knowledge of the position vector and the 3x3 metric of the rotation metric. And yeah, the rotation metric, we also can obtain the inverse of the rotation metric. And today we will know why we need to obtain the inverse of the rotation metric. And when we compose the homogeneous transform by 4x4 metric, one reason that we need to compose this complicated metric is that we compose it because when we compose it in this way, we also can obtain the inverse of the homogeneous transform. The idea of how we need to obtain the idea of why we need to obtain the inverse of rotation metric and the homogeneous transform metric is that sometimes you want to relate the endpoint frame to the base frame. You may obtain the homogeneous transform to continue that, but sometimes if you want to obtain the base frame as respect to the endpoint frame, maybe you need to talk about the inverse of the homogeneous transform. So before moving on, yes, industrial manipulator have link in series, which means we may have a base, have a link, and have a link, and have another link in series. But this link in this picture, the things are on the plane, but in the actual robot, the robot is in 3D space, but the robot are connected by a series of links, and the links are connected with each other by joint. This is joint, joint, and joint. And if you have seen some robot, the joint of the robot can be rotated, and we put actuator to drive the joint of the robot, and it means that we can make the robot move by drive the joint of the robot. And in the same time, if we want to control the position at the endpoint of the robot, if we want to control the position, at least we should be able to measure the angle of each joint. We need to measure the angle of each joint. So the robot, the joint is driven by actuator, and the position of the joint need to be sensed. Positions means the angular position. If the joint of the robot are the level joint, but in our class, in some example, we also talking about when the joint are the prismatic joint and have the linear motion. The joint position in that way is also in the linear position. We also will talk about that in next week. And yeah, for the industrial robot, in general, the base frame is connected to the stable surface and doesn't move. And on another end of the robot, we usually attach the endpoint of the robot by a tool or a kind of gripper to manipulate the object or to handle the task that we apply the robot to. And yeah, the slide kinematic of manipulator. Now we got the brief explanation, and we can figure out what is the things that like manipulator that we are talking about. How about the kinematics? So in our class in the industrial robot 1, yeah, we can talk about the mechanics of the manipulator, but in our class we only focus on the kinematics, which means we only consider about the motion of the robot, and we are not talking about the force that create the motion, which means we are mainly consider about the theta 1, theta 2, and theta 3 that create the shape of the robot in the instant of time. And also we consider the time derivative of the joint when we obtain the first time derivative of the joint, and also the second time derivative of the joint. And these are in the joint space. We also sometimes talking about the position in the Cartesian space. It seems like in our application, we mainly want to control the position, the velocity, and the acceleration of robot in the Cartesian space. But what we can do on the robot, what we exactly can do on the robot is to try to control the joint variable, the joint position, the joint velocity, and acceleration. So the main objective of this class is to provide you the mathematical tool that's required to relate this to space coordinate, from Cartesian coordinate to the joint coordinate. But yeah, for kinematics, we only consider about the angle, velocity, and the acceleration. And yeah, the robot system are complicated in the actual use. In order to obtain the position, the velocity, the acceleration we want, we need to consider the inertia, the friction, and the stiffness of the robot, and the gravity, the effect of the gravity, and try to consider how much torque we need to drive to each joint so that we can get the speed we want, the acceleration we want. But for the basic study in this class, we mainly focus on the kinematics. And yeah, the degree of freedom, many times our lecturer asks you how many degree of freedom of this system. So for the industrial robot, most robots are designed and the mathematical tools are developed for the robot. And I think it's not so complicated to count the degree of freedom of the robot. The basically the degree of freedom is counted by the number of the joint of the robot, the number of the actuation unit of the robot that can provide the change in the position of that robot. So it includes the theta that the level load actuator, the rotational actuator, drive the joint, or it also includes sometimes when we change the displacement in the prismatic joint if the robot has the linear actuator. But the number of degree of freedom in the industrial robot is equal to the total number of the actuator that drive the joint, the total number of the joint that are driven by the actuator. For example, in this picture, we have the first joint driven by one actuator to control the theta 1 and another one to control theta 2 and theta 3. If we consider only these, we may have like 3 degrees of freedom for this robot. And yeah, last week we have how to say, I think you already heard about the forward and the inverse kinematics. But again, the idea of the forward kinematic is, hey, if we know the joint angle, theta 1, theta 2, and theta 3, if we know the joint variable, how can we obtain the position at the endpoint or at any link of the robot in the Cartesian space? How can we link the theta 1, theta 2 to the x, y, z of each link or at the endpoint? And for the inverse kinematic, the problem is like inverse. If we have a desired position, of the robot, we want the robot to go to pick one thing on a table at a position X, Y, Z. How can we know that? How can we know that the robot should be in which posture? What is the corresponding theta 1, theta 2, and theta 3, so that the robot can go to the position we want. But we said that the inverse kinematic is a more complicated problem because sometimes it has multiple solutions. The most simple idea is that if you have the 1-2 link manipulator on a plane and you need to drive, the robot has a 2 link on a plane, right? Has L1 and L2 as a link length, and the theta 1 is the angle that the first link make with the x-axis, and we have the theta 2 where the link 2 have the angle with the first link. With this, if we want to obtain the xy coordinate at the endpoint, it's not that difficult, right? For the forward kinematic, you can obtain the L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, and this will equal to the x coordinate. And for the y coordinate, we also do in the similar way. So this is the forward kinematic. If we know the theta, it's not difficult to know the xy coordinate. But if we say that, hey, we want the robot to go to the xy position, what should be the angle of each joint? What should be the theta 1 and theta 2 that make the robot go to the xy position? If we put the problem in this way, the complication comes from the fact that the robot sometimes can have alternative solution. In the first posture, we have the link of the robot in this orientation. It's also possible that the robot can be in this shape and it still can go to the target position. So the problem of the inverse kinematic, not only we need to solve the mathematical problem, but we need to find the total number of the solution that we can obtain. So it's a more complicated system, more complicated problem. And if we only talk about the forward kinematic and inverse kinematic, we are talking about the point or the target position that the robot need to go to. But if we want to say that, hey, if this robot need to move from point A to point B, if the robot need to move from point A to point B, now the current position is point A, and the robot need to move to point B. It seems like it has infinite way to go. It's not only the endpoint move like as a linear path to go to the target position. It can go in the curved path or some like different curve to go to that part. In the world space or in the Cartesian space, yeah, we want to see it move in a linear way because it seems like it's a shortest part, shortest distance to move from A to B. But the robot, when the robot moves, it doesn't move by the XYZ, but it moves by the theta 1, theta 2, theta 3. So the thing that the human likes, because the human can see the change in position, the human may prefer XYZ, and many times they prefer the shortest XYZ move. But is that really good for the robot? Because the robot moved by the theta 1, theta 2, theta 3. If we ask the robot may prefer to move with a shortest possible angle of them, right? Because it consumes time to move each joint by the actuator. It consumes time and energy to spend to the actuator. If we ask a human may want to see the thing that he can see. He can predict it in the real world coordinate, in the X, Y, Z coordinate. But if we ask the robot, maybe the robot may prefer to go by the shortest position change in that joint. So this is the problem of the trajectory generation. And yeah, maybe if we want the robot to move from the coordinate x1, y1, and c1 to the coordinate x2, y2, and c2. Maybe if we plot the joint angle, the joint position or the angle varying by time, maybe it have the theta 1 and theta 2 to go to the xy position that we want from x1, y1 to x2, y2. At least we know that at the target position and the initial position, we know the x1 and x2 that we want from the inverse kinematic. We know that in the beginning, the theta 1, theta 2 is in which angle, and we know that if it want to reach the target position, it need to go to somewhere in the angle that we know. And we can like control the joint of the robot to move to that target position, and we can go to the target position in the XYZ coordinate. But if the robot move in this way, when we see the robot move by eye in the XYZ coordinate, sometimes we cannot see it move in the linear part. So if we want it to move in the linear part, we have some theory, some mathematical tool to generate the part of the theta, so that in the real Cartesian coordinate, we can see the robot move as a linear or move as a curve that we constrain the radius of curvature, something like that. Until now, we only talk about the position. In terms of velocity, we also have many things to work on. For example, we know that from the initial theta 2 to final theta 2, it needs to move from this angle to that angle. But how fast it needs to move, how should be the acceleration from the first point to the final point, when it should accelerate, when it should decelerate to the zero velocity at the target position. So I hope until we complete the industrial robot 2, we can have an idea how to solve this problem. And yeah, I need to say something like, in our class now, it seems like I am assigned to teach the theory of the industrial manipulator, and Ajahn Pongsan is teaching about how to program ROS for a mobile platform. But in order that you can see the real thing that we study in the class, I'm planning to build one prototype of a low-cost zero robot, so that maybe after you study the content in my section, and after midterm, when we study about the inverse kinematic, maybe at that time you will have enough tool to solve the problem Like if we want the robot to move to this position in XYZ, we need to change the joint angle to theta1, theta2, theta3, something like that. So I will try to prepare one small hardware kit for you to come to program and move the robot arm to the target position. And yes, talking about today, as I mentioned in the beginning, that many times we will see the metric operation in our lecture. And yeah, from this slide or the slide, you need to see something stupid like this, like A, B, C, and have the superscript, the subscript. So before jumping to that, let's see the thing to give some explanation before you see the real equation. So yeah, if we talk about this, the letter with the bold letter frequently means the metric or the vector, but the letter without the bold, the normal letter are mainly usually be the scalar quantity. But yeah, in this case, for example, R is the bold letter. It means the rotation metric. And the second important thing is this one. This one is the leading superscript, which is the superscript that comes from the letter. In the left top of the letter, the leading superscript always be the reference frame. In this case, it means the rotational metric that respect to the reference frame A. This is a position metric that respect to the reference frame B, like this. And how about the trailing subscript? The trailing subscript is this one. Sometimes in this case, for this case, it means the vector, the position vector of the frame B as respect to the frame A. But for this, the meaning is the position of the origin point of the frame B, which respect to the frame A. So it's still complicated, right? But this slide just the introduction. You don't need to remember all the things because now you still don't know what is the meaning of the equation. So it's not easy for you to get the meaning of what is the position of the B origin with respect to A. But the objective of this slide is to let you know that, hey, if you see the leading superscript, it means the frame that we reference to. And if you see something like trailing subscript, it may be the point that we consider or the component. And yeah, and on the top right here, it always be the arithmetic manipulation. It can be the metric transport T, or it can be the inverse of metric, something like that. And the concept of the metric representation for manipulator is that all the object on 3D space can be described by its position and orientation. If you hold one pen on your hand, that pen on a 3D space, you can describe the pen by its position. The position may be the position of the pen's center of gravity, or maybe at the pen tip, anywhere on the pen, but you're gonna set that at a reference of the pen. So the pen can be described by the position of that point on the pen, and also the orientation of the pen. Does that make sense? So all the things in 3D space can be described by its position, but its position may be its center of gravity's position, its tip position, or its handle position, any position on it. And another information that we need to know is the orientation of that object. Yeah, you may can say that, hey, Ajahn Ronnapee's car now is in the front gate of Chulalongkorn. Now you are indicating my car's position, and then you can indicate my car's orientation by, now Ajahn Ronnapee's car's direction is going toward like 20 degrees from the north to counterclockwise direction, something like that. It's the orientation information. And object in our class, object of the industrial robot may be a robot link like this. A robot link can be an object. A tool or gripper of robot can be an object. And a stationary base can be an object, a base. And also a table, something like that, can also be an object that we consider. But the idea is, if we want to know an object here, we know its position. We know its position by a position vector that describes this position. And we know its orientation. How can we know its orientation? We need to find some way to relate the direction of the X palm, Y palm, and Z palm to the global position that described by X, Y, Z direction. So to describe the orientation of an object, we need to know that, hey, the X palm axis make the angle with the X axis with one angle, make the angle with the Y and the Z axis with another angle. With this, if we know that the X palm axis make the angle with X, Y, Z with a specific angle, with this method, we can tell the direction of the X palm direction. It also for the Y palm direction. If we want to exactly tell what is the direction of the Y palm, you need to tell that, hey, the direction that the Y palm make with the X axis, make with the Y, and make with the Z axis is what is the angle that the Y palm make with this axis. So for example, the simple way, we have X, Y, and Z axis, right? If we have the X palm with the angle of alpha with this, and Y palm, also make the angle alpha from Y, but the Z palm is still in the same direction with the Z. In this case, hey, you can give the information that, hey, the X palm make the angle with the X axis of alpha, and x prime already make the angle with the y of the global as 90 minus alpha, and x prime make the angle with the z axis, the global z axis of 90 degree. 90 degree. So if you only tell this, x prime make an axis of alpha with x, make the angle of 90 minus alpha with y, and make 90 degree with the z axis. With this, you can only draw the x prime in this direction. You cannot draw it in the different direction. Just only one direction possible with this condition. And what if we want to tell the information of the C prime axis? The C prime axis make 90 degree with the global x. The C prime axis make 90 degree also with the global y axis, and it makes 0 degree with the global z axis. So with this description, the direction of the C prime can only be in this direction. So the idea, how can we tell the direction of the frame, is to try to tell the angle between the direction of that frame as with respect to the direction, to each direction of the global frame. We will see in the detail in the following slide, but this is just the concept of how to tell the orientation, how to describe the orientation of the frame or object. But we attach a coordinate frame. We attach a coordinate frame rigidly to the object, which means here we put the coordinate x prime, y prime, and z prime rigidly on an object. Here the object is a screw on a table, which means that if the screw moves by 10 centimeters, our frame is also moved by 10 centimeters. If the screw rotates about the y prime axis by 10 degrees, our frame also rotates about the y prime axis by 10 degrees. So we are not talking about an object anymore, but we will talk about the frame that attached to the object. And our point on the object is described through the attached frame. So in the picture, we know that for here, the origin of the frame, is put somewhere in the center of the head of the screw. So if we want to describe the position of the tip of the screw, we can say that, hey, this tip have the position of x will be 0, y will be y prime, and z will be 0. For example, because now the screw is something like this, the screw is something like this, and we put a frame on the screw when x is like this, and y axis is like this, and z axis like this. So in this frame, x prime, y prime, and z prime, the center of the coordinate frame is 0, 0, 0. And yeah, the head of the screw is at the 0, 0, 0. And how about the tip of the screw? If the screw has the length of L, so at this point, the position of the tip will be 0, L. and 0, right? 0 I0. No. Come on. Yes, 0 L0. That's better. Thank you. Okay, so 0 L0. Correct. And how about this bullet? Position and orientation of the frame. Okay, so we already said that, hey, instead of talking about the screw, now we are not talking about the screw anymore, but we will talk about the frame that we attach to the screw. And then we know the information that how is the point on the frame, how is the point on the screw relate to the frame. Also, when we want to relate our frame, the position and the orientation of the frame, the position and orientation of the XYZ plane frame that respect to the global XYZ. If we know the relationship between these two frames, and we know how the object, how the particle on the frame is related to that frame, finally we can relate the particle or the part of an object in the global coordinate. So the idea is we relate an object, the point on an object, by a frame that attached to that object. And then we relate the frame, this attached frame, to the global frame. And then we can have the global position, global orientation of the object. Why we need to do in this way? I mean, why we not like directly relate the object at the endpoint to the global? Yeah, when we see this system by eye, it's simple to tell that how far in the x direction the object come from the origin of the global, how far the object far from the origin in the y direction and in the z direction. It's easy to say that. But in the real application, you may only have a camera on the endpoint, and your camera just only can measure or estimate the distance between the camera and an object by what the camera see. So we can only know the distance of the object as relative to the camera by the XYZ of the camera. And we need to relate it to the link formation so that we can get the global position of an object. Also, maybe if the robot tips have a force sensor and the force sensor on the robot tip touch with some object, we can only measure the force in the XYZ direction of the tips or of the force sensor. In order to relate the force to the global direction, we need to use this mathematical tool to relate. We already said that the metric representation of a rigid body is described by attach the frame on an object. And yeah, the frame that is attached on an object will be represent the body of that object. And the position and the time derivative of the position, which is the motion of the frame, can completely explain the motion and the position of an object. And in order to give the fully explanation of a frame. Now we know that the frame can fully define an object. Now we know that the frame can fully define an object. So how can we define the frame? We need two information to define the frame. The first information is the position. This means frame A. This means frame B. So this is frame A, and this is frame B. This means the position vector that respect to the frame A. Respect to the frame A means consider in the X, Y, Z component of the A. To define, to give the description of the frame B, the first thing we need to know is the position of the frame B origin with respect to frame A. The position of the frame B origin with respect to frame A. So in this case, we can get like the XYZ coordinate of the frame B origin, right? And the XYZ coordinate is in like XI, YJ, CK. If we write the position in the term of the vector, the position vector of the B origin can be described in the terms of the vector XYZ in the unit vector IJK, which correspond to XYZ direction. But in our class, instead of write the position vector as XI, YJ, and CK, we will write the, I already mentioned that if we write P in the bold letter, it means a vector. And instead of writing the vector component IJK in this way, we write it in a metric form. Like this, 3 by 1 metric or vector metric. This is the position. We need to define, we need to describe the position of the B origin with respect to the frame A. And we need to describe the orientation of all the axes of the frame B with respect to the frame A. So we already know the idea. How can we define the orientation of the coordinate frame B? So for the coordinate frame B, we also have like maybe XB unit vector, YB unit vector, and ZB unit vector. The global frame have I, J, and K unit vector. If we want to give the explanation of the orientation of the frame B, we need to try to find a way to tell the information of how the XB, how is the angle the XB make with I, make with J, and make with K. How is the angle of the YB make with I, make with J, make with K. And also how is the angle the CB make with I, with J, and with K. If we give this 9 component, 9 relationship in a metric. We can give fully description for the orientation of the B frame with respect to the A frame. And this is the concept. And in the next slide or the following slide, we will see how to compose this 9 components of the metric. Again, the position vector is simple, right? The position vector, position of this point with respect to the frame A. Position of this point with respect to the frame A is, yeah, it's not easy to draw, but I will try. It should be something like, is that good to be like this? So it have the py in the y direction, have the px in the x direction, and have the pc in the c direction. And yeah, this is correspond to the unit vector I, j, and k of the x, y, and z. So the position vector is simple. Before this, we may study that the position vector is equal to pxi plus pyj plus pck. And in this class, instead of the vector, we write it like this. And this this component we write in a 1 3x1 metric. If a metric have 1 column, if a metric have a 1 column, is a vector. And this is a position. It's nothing complicated for the position to compose a metric for a position. How about the rotation metric to describe the orientation? I already give you an idea that, hey, we need to give the information that how the x position of the B frame make with the x position, make with the y position, and make with the c position of the A frame. So in this xb dot xa unit vector of xb dot xa is equal to the magnitude of the unit vector of xb multiplied by the magnitude of the unit vector of xa and cosine of one angle. So the magnitude of the unit vector is 1, and the cosine of the angle give us the information how is the angle between that 2 unit vector. So this is an idea. So each component will be the direction cosine of the 2 unit vector. So each column tell the information of how the unit vector of the frame B respect to each unit vector of the frame A. And yeah, if you see here, the alpha may be the angle between the XA and XB, so that this component is described by this. Again, in this slide is still the concept. You still not have a clear idea on how to use this, but follow the concept first. This is the idea of the rotating metric that describe the orientation of the frame. There is one property. They said that, okay, before jumping to this property, we need to go slowly. How can we compose this metric? Okay, one more time. How can we compose this metric? The rotation metric of the frame B respect to frame A is equal to how the unit vector x of the frame B, make with the x of the frame A, make with y of the frame A, and make with c of the frame A. The x component of the frame B already fully described. How about the y unit vector of the frame B? YB, and YB. How the YB make with the x frame A? How is the angle of YB make with the x of the frame A? How is the angle YB make with the y of the frame A and make with the z of the frame A? And the last one, the unit vector in the z direction of frame B. The unit vector in the z direction of the frame B. How it make with the x of the original frame A, y of the original frame A, and z of the original frame A. So here is how we compose the rotational metric of B with respect to A. Okay, how about this? How about A with respect to B? Can we compose the rotational metric of the A with respect to B? If we want to do A with respect to B, we need to begin with the x component of A, and see how it make the angle with the x of B, y of B, and z of B, right? How the y vector of A, make with x of B, y of B, and z of B, and how the z unit vector of frame A make with the z of frame B. A respect to B. And yeah, these are the same. This is B respect to A. How about if we want to know B respect to A? Transport means we're gonna change the row to column and change the column to row, right? So this is okay, this is the same one. This is the same one. Is the rotational metric of B respect to A. If we want to obtain the rotational metric of B respect to A, transport in the column should be row, right? The column should be row. So xb dot xa and xb dot ya and xb dot ca. Here we change the column to row. And how about change the second column to the row? We have yb dot xa, yb dot ya, and yb dot ca. You will do by yourself for the last column, transform it to the row. But this is the rotational metric of B respect to A, transport. And this is the rotational metric of A respect to B. Can you see something? Can you compare these two metrics? Do you see something? Finally, these two metrics are equivalent. So the rotational metric of A respect to B is equal to rotational metric of B respect to A with the transport. And if we obtain this product, I won't derive this because it's super long, but if we derive this, we will get the metric, the unit metric, which means the rotational metric of B we know that if the metric multiplied by its inverse, we will get the unit metric. So not only the B referred A refer to B equal to B refer to A transport, but the transport itself it also equal to the inverse metric. So many times we need to obtain the inverse of the metric, but the rotation metric is a special case that the inverse is equal to the transport, so we don't need to spend our much effort to try to obtain the complicated inverse of the rotation metric. We just do the transport and we can get the inverse of the metric. So yeah, this makes our life easy in this way. In the following slide, we may see why we need to obtain the inverse of the rotating metric. But at least we know that we don't need to compute the inverse metric. We just do the transpose and we can get the inverse metric. So we see that for here, to compose the rotation metric, we need to obtain the dot product of 9 components. We need to obtain the dot product of 9 components. But you may have experienced, you may have heard that, hey, to describe one thing in the global 3D coordinate, we need 6 degrees of freedom or 6 variables for fully describing that things on the 3D space. So in general, we describe the position of the things in the 3D space by 3 degrees of freedom, X, Y, and Z. And we need more 3 degrees of freedom to describe the orientation of that things in the 3D space. But why? Now, for the rotation metric, 3 by 3 metric, we need to obtain 9 components of the metric. But in the physical meaning, only 3 components, only 3 variables should be enough to explain the orientation. But why? When we compose the rotational metric, we got 3 by 3 or 9 components. It seems like we should have a simple way to describe the orientation. And that things we call the alternative representation. Alternative representation give the same information with the rotating metric, but only 3 components, only 3 angles is enough to explain the 9 components of the 3 by 3 metric. Only 3 number of angle is enough to compose 9 components of the 3 by 3 metric. Before jumping to the next page, imagine that we have the frame A, which is the global frame, the original frame. And we have one arbitrary frame B. And of course, the frame B is different from the frame A. The frame B share the origin with the frame A, and it put on the same position in the beginning. In the beginning, we have the frame A with the X, Y, Z. And we also have the frame B. And the frame B, X, A, Y, A, Z, A. And the frame B also share the same direction of each component with the frame A. But after that, the frame B rotates with a sequence of rotation. A sequence of rotation have 3 steps of rotation. For example, we rotate the frame B about the x-axis of frame A. What happens if we rotate the frame B about the x-axis of the frame A? The x-axis of the frame B still be the same. But if we rotate the frame B about the x-axis of the A, the z-axis will change the position, and the y-axis will change the position. If we rotate the frame B about the x-axis of the frame A, the xb still keep the position, keep the direction, but the direction of the yb will shift to yb prime, and cb will shift to cb prime. This is just one step of rotation, but what if we do the 3 steps? We can get something related to the rotation metric, but there are 2 parts. I mean, a sequence of rotation in this class, actually they have many type of sequence, but the important sequence that we need to know in this class, a sequence of 3 steps. We have the XYT fixed angle sequence and the ZYX Euler angle. For the fixed angle, the concept is they rotate about the axis of the frame A, which never change the direction. The frame A never change. In the beginning, we rotate about the x-axis of the frame A, then we rotate about the y-axis of the frame A, and then rotate about the z-axis of the frame A. And of course, the axis of the frame A never change the direction. For this, we call fixed angle. The second alternative we call Euler angle. Euler angle is a little more complicated. We rotate the B coordinate about the A coordinate. We firstly rotate about the Z axis of the B frame. And then the B frame already transformed from the original position, original orientation. After that, we rotate about the Y axis of the B frame. When we rotate first time about the Z axis, the axis of the B coordinate, B frame already changed. Then we rotate about the Y axis of the B frame. It already changed again. And we do rotate about the X axis of the B frame again. So the difference between the fixed angle and the Euler angle is that for the fixed angle, we relate to the direction of the axis of the frame A, which never change. But for the Euler angle, when we rotate one time, it changes the direction. And we do the rotation about one axis after it already changed the direction. Here just introduction, but to let you get the idea, it should be in this slide. Do you need 10-minute break before come back? Or you want me to continue this slide first? No response. So maybe we're gonna continue.
พักก่อนก็ได้ครับอาจารย์ผม
Okay. Okay, so 10-minute break and come back by 2:40, okay? 2:40.
โอเคครับ
ครับ
ครับ